Hey, my name is Brennan, and I'm going to be taking you through topic-sensitive PageRank. So PageRank is essentially Google's search algorithm that's used to sort different pages. So basically sort them by importance. So think when you search a certain topic, right, it'll kind of, this is what the metric they use to rank which links come first, second, third, and etc. So the big idea for this is that you have a random surfer who essentially will click a link at random. So this is kind of like a random walk. So it's randomly walking through that link. And we use that to measure page importance. And it's very much based on the graph theory that we use in class, as it kind of works a lot with digraph edges and using those to rank pages. So the first part of this is that it represents the World Wide Web as a graph. So just like we had in class, right, you have a graph with vertices and edges. Each web page is a vertice, and each edge is a hyperlink, so a link to another page. If page U links to page V, then that gives us a directed edge, so from U to V. So that makes it a digraph. Additionally, you have the out degree N sub U, which is essentially the number of links leaving page U. So this is the PageRank algorithm. This is the initial version. So the initial setup, we have a page V with a link from U to V, and it starts with a rank of 1 over n, where n is all of the vertices in the graph. Um, Additionally, we have the iterative update formula. So essentially how this works is for each vertice, right, you are going to sum up the rank of the kind of the vertices of an incoming edge. So basically, let's say you have a web page V with 3 pages linking to it. You're going to take the rank of those 3 pages, sum them up, and then take it all over n, which again is the number of vertices. A page rank is going to be equal to the sum of the page rank of the pages linking to it. So now we're just going to take it and put it into matrix form with eigenvectors. So essentially the matrix representation of the previous equation is going to be rank sub I plus 1, so just the next iterative rank, is equal to m dot rank sub I. So in this case, m is a matrix representing link probabilities, which is essentially the probability that a random surfer on page J will click the link to page I. So as you can see, with the eigenvector equation, we have a dot v equals lambda dot v. And so in this case, the um, the purpose of this equation is that with lambda, it's only used to scale. It's only used as a tool of magnitude and not as a change of direction. Um, so at convergence, we kind of have this as r equals m dot r, because we know from just the threshold, once it converges, the R's, which is essentially the ranks, are basically equal, whether it's rank sub I or rank sub I plus 1. And so now we have the damping factor. So the big problem with this is that you have disconnected components. So the graph is not connected, and there also may be the presence of periodic cycles that can prevent convergence. So just after a certain amount of steps, if it keeps kind of iteratively going back to the same page, there might be an issue. So to fix this, we add a teleportation factor with a probability of alpha. So in this case, we take m prime, which is using the new m of the last equation, and we're going to have. So now we have calculating the topic probabilities. So essentially this means given a query Q, what is the probability it belongs to topic C sub j? So first we have the probability of C sub j, which is the traditional probability of topic J kind of appearing in a certain query. Um, and we have Q prime, which is basically you have the normal query Q prime, which is kind of similar wording, similar verbiage, things like that. And then we have the likelihood of query words given a topic. So for the probability of Q prime given C sub j, we basically multiply all the probabilities of Q sub I, which is essentially all the different queries and just kind of query forms that we have given C sub j, which was given before. And so this gives our final computing query score. It should be S sub QD, which is basically the equation we just calculated. You kind of do it for every value of j.